Benoît Combamal. I'm going to chair this session where we have three different papers on a session entitled Empirical Studies and Experience Reports. Unfortunately, the first speaker didn't made it for joining us in person, so he will present remotely, and the two other papers will be presented in person. The first paper will be presented by João Saraiva, a paper entitled Trading Runtime for Energy Efficiency, which is one of the hot topics that we have currently in the community with regard to the language that we are developing. So I'm super eager to hear from João. So João, can you hear us?
Yes, I can.
Okay, excellent. So you can start whenever you want. The floor is yours. Thank you very much.
Okay. Well, thank you so much. First of all, I want to apologize for not being at Pasadena. Last week I was almost crying when I got to know that I didn't have the visa to enter US. So it's not the first time, as I will see so in my third slide. So I'm going to present this work that was mainly performed by two master students, Simão and Luís Silva, in the context of the course that we run here on software language engineering at Minho University, and is co-authored by Paulo Fernandes, that is now at New York University in Abu Dhabi. So, in 2017, actually, I missed SLE again. For very sad reason. My mother passed away 2 days before I flew to Canada to attend SLE and to present this paper about defining or trying to understand the energy efficiency of programming languages and answer this question: does the choice of programming language influence the energy consumption of our programs? And we had some intuition. Of course, we all have some intuition about is this language fast, is this language slow, is the interpreted language slower than a compiled one, but we wanted to have numbers, but also to have numbers in terms of energy efficiency, okay? Which paradigms are more energy efficient? We had a lot of questions that we couldn't scientifically answer. So we developed a ranking, okay? That was our paper that was not presented at SLE 2017, so 7 years later, the main result of that paper is being presented at SLE. That I'm a bit happy for that. So this is the ranking we compiled. We considered 27 programming languages, and there are some curious results, like something that probably most of us were expecting, that C is the fastest, but also it's the greenest, so the most energy efficient language. But there is also some results that we were not expecting to have this gap or this difference in performance, both in terms of execution time and energy, with a language that are very popular nowadays in industry and in academia, like Python, of course. So so we have these results that a program that consumes 57 joules of energy to run our benchmark would consume 4,600 joules in Perl, and similar in Python. Okay, the same in terms of execution time. Some program, our benchmark suite that would run in 2,000 milliseconds would take ages to perform in Lua or Python again. Okay, so it was a bit surprising for us, and we also divided these results in terms of the architecture, the language we were using. The compiled language we were expecting it was faster and more energy efficient than the others, but also virtual machines are a bit slower, consumes a bit more energy, and of course interpreted language are the slowest and the most greedy language. So this is the result of the paper we published in 2017, and but if we think in terms of a car, okay, because our hardware and operating systems and language and compilers and benchmarks are were developed or focused on runtime. And if we wanted to save energy, we all know that when you drive a car, if we want to reduce energy, we have to reduce, or of course we can use the brake, but if we brake the car, what we are reducing is the revolution per minute of the engine, and we know that if we reduce speed, that is the consequence of that. Of course, we reduce energy consumption or fuel consumption. Of course, we also know that we increase travel time. Okay, in terms of software languages, the intuition that most of people in the beginning I was asking is that a faster language is always a greener one. So that goes a bit against this car intuition we have. So our question here is, can we expect a similar behavior when using power capping? So can we reduce energy consumption of a language by imposing some limit on power of the CPU? Let's say, we put some limit on the revolutions per minute of our engine, and that was the question I asked the students in the course. And so that of course, immediately there come a lot of questions. Can we reduce energy consumption of a program by defining a limit on the power usage? How is the program's runtime affected by defining such a power cap? So are we expecting to reduce energy, but at the same time to increase execution time, like in a car? We reduce fuel, but we increase travel time. Are software language affected by a power cap in the same way? I might think that if I reduce the RPMs in a Ferrari, probably I save more energy than in a Fiat 600. But probably, although I reduce in percentage more fuel, of course Ferrari is much more than the other. And what happens in terms of energy and are all the languages or the programs affected in the same way by a power cap? And does our previous ranking of programming language, energy ranking of programming language, be affected by the power cap or not? So those were the questions we wanted to answer in this work. And so we started with okay, we are going now to measure again the same benchmark we use for our initial ranking. So we consider the computer language benchmark game. We consider 9 out of the 13 problems there, and I think 9 because 3 I think we didn't consider because there was some parallelism and threads involved, and we didn't want to enter to see how that affected our programs. So we wanted not to consider concurrency nor parallelism. So we consider 9 out of the 13, and we consider 20 programming languages. So we also define language-specific benchmarks. So we analyze 3 benchmarks that consists of the da capo in Java, no-fib in Haskell, and PyPerformance in Python. So those are language widely used in academia, in industry, and they presenting different programming paradigms and execution models. To measure energy, we relied on RAPL, Intel's RAPL framework that estimates energy consumption. There are some studies showing that it produces precise or accurate measurements. And the nice thing about RAPL is also it supports power capping. So we can define a cap on energy to run our programs, a cap on power of the CPU. And of course, we had to reduce the process of the operating systems to the minimum possible. And executions, we also use the temperature sensors that are available in a Linux machine and that to start each execution of the program at the same temperature, so in the same context, because the temperature of the CPU, of course, influence energy consumption. So we always start in the same context. So if we think in terms of, okay, let's compare programming languages. Oh, sorry, I have to port these slides from well, a different system, and it's not correct. But so we have to consider different programming languages, and we are considering 20 programming languages, and it's not. So we have to write programs in all these languages. So probably I'm familiar with the 3 of those 4 here in this slide: C, Java, and Haskell. But even if I have to write the same program to implement the same problem in one of these 3, I would be more, let's say, familiar, or I'm more familiar with 1 or 2 of them that probably will influence my solution. So we rely on the computer language benchmark game. Although it's a game, it has been used in research work in several contexts. And the nice thing is that it's a project to compare programming languages focused on performance, and the performance in that time was runtime and memory consumption. It consists of 28 programming languages, as I said before, 13 different benchmarks, and the experts from the different languages were asked to implement the fastest solution for those 13 problems. They rely on the same algorithm, and everything, the nice thing is that everything is available, the source code of solutions, compiler versions, optimization flags for compiling and run the program. So those are the 28 programming language there, and the 13 problems. And those are the 20 programming languages we consider with the compiler versions we used, and the 9 different benchmarks we consider in our work. Okay. So for the measurements we use for the energy, as I mentioned, we use RAPL, that is supported by most modern Intel architectures, okay, and gives precise measurements of the consuming of in-chip GPU and the RAM, CPU, and the packages, the overall consumption. It provides support for power capping, that was important in this work, and for time we use the Unix time tool. So, because I think we can easily agree that different cards have different, let's say, minimal revolutions per minute for the engine to work. It's the same with hardware, so we have to calibrate the power capping. So we execute benchmarks with different values for the power capping, 2, 10, 15, and 25 watts, to see which one would produce, for this particular hardware where we run the experiments, produce the most energy efficient executions, and that was with power cap of 15 watts. So we did some calibration in the beginning. Okay, we run this on a Linux machine. Everything is available, publicly available. We had to compile 108 programs to run them, to measure the energy, and so we had a lot of results. So this was more or less the results of 1 week of our computer running. And so these are the results. So this is the impact of energy for the 20 programming language. So this is the average of energy savings for the 9 benchmarks we use from CLBG. So all language decreased energy consumption. So the Julia is the one that decreased the least, so it was 6%. The average of the 9 programs running, it consumes 6% less of energy with power cap. Haskell was the language that saved most energy with the power cap, 25%, compared to running those programs without power cap. And the average was around 27%. 13%. So on the opposite is the impact on runtime. So of course, if we define a power cap, we are, let's say, reducing the frequency in some way of the CPU. So we are increasing the execution time. And again, Julia only increased 35% execution time. There are several languages that increase more than 100% of the execution time of our programs. So in fact, we are trading runtime for energy consumption. This is the ranking of our 20 language .port capping. So this corresponds to the ranking of our original paper in 2017. So it's without power capping. So the ranking is very similar to the one we presented before. And I have to say that we are running this in a different hardware with different compiler and interpreters for this language and virtual machines, of course, and also with a different version of the operating system. But the ranking itself, it follows more or less the same order. So this is the ranking with power cap. So there are errors upwards and downwards with positions compared without power capping. So only 6 languages change position in our ranking with power cap. Okay, and again, C is very efficient, and I always have to talk about the ones that are not as efficient as C. Interpreted language like Python, Perl, Ruby are consuming much more energy and runtime when compared to C. Power capping. So the conclusions from this first study is that power capping reduces energy consumption in all the programming language and in all benchmarks, CLBG benchmarks. Okay. Around 14% across the 20 programming language in average, and also increase the execution time in no language and in no benchmarks. Okay, overall an increase of 91% of execution time, without single exception. For all language, all programs, we had reduced energy and we increased runtime. So we also try to validate these results, because we can always think, who is LBG representative? And I fully agree. Yeah, you can ask me this question at the end. How representative are the benchmarks of the LBG? They were developed, or first they were asked for experts, so let's say advanced programmers, probably they are not regular programmers, and also focus on speed, on execution time. So they can be polluting our results. So we try to more realistic benchmarks specific for each language. So with DACAP for Java, Python, or PyPerformance for Python, and the NoFib for Haskell. We run these benchmarks exactly in the same context we did with CLBG before, same hardware, operating systems, same measurements, and also the same value for the power cap, so the 15 watts. Okay, and again, with DACAP we can see that also Java consumes in average 13% less energy in all programs. Is the case, consumes less, in average is 13%. And in terms of runtime, it increased runtime by 110%. Okay. In terms of PyPerformance, with very few exceptions, PyPerformance programs also trade runtime by energy efficiency. I think there are 5 or 6 exceptions here, but they all save energy with power capping. In terms of the NoFib, there are no exceptions, so all programs reduce energy consumption and increase execution time. So for this second study, we can see that in average we have energy saving of 80% from NoFib to 21% from the DACAPO benchmark, and the increase of execution times goes from 21% from the ASCL no-fee benchmark to 46% to the DACAP one. And those results are following more or less the ranking we define in CLBG. First is that all programs in all programming language reduce energy consumption. For all benchmarks, energy decrease while execution time increases, with very few exceptions in pipe performance. And again, in Java, the results follow the results we had in CLBG. The same in terms of the energy we saved in Python. So, from this study, what we learned is that faster is not greener. Probably it's unexpected or expected result. Depends on point of view. But all programs save energy, but by running slower, with 5 or 6 exceptions in Python. Okay, my supervisor during my PhD, I was doing a PhD in ASCL, and that time it was not as fast as it is now. And he was sometimes he was telling me that speed up is not speed. And I think the point here is that green up is not green. Okay, for instance, in ASCL is in terms of saving energy with the power cap. ASCL is in top 1 of energy savings. It saves 27% of energy compared to not using power cap, but in the overall ranking is still in the 11 position. Okay, and C is still the fastest and the greenest language with or without power capping. So we did this work under this green software lab that we started here in Minho some years ago, or more than 10 years ago already. One of the results is this ranking and the previous one, but also in terms of energy, let's say energy aware, we adapted a lot of techniques like smells, fault localization, technical depth, all these concepts to green. So if you are interested, you can see it in our webpage. So I'm really happy to answer your questions now.
Thank you very much, João. Is there any question in the room? Yes?
Yes. Yes, thank you for the talk. It's very interesting to see the different languages and how they perform. But I think there could be a third dimension, or maybe it's also the fourth, I don't know, but in terms of how these issues are implemented. So in software engineering, we often apply some explicit guidelines, so design patterns or something like that, which, well, directly impact how the program executes. For example, a visitor pattern helps us in the ways of thinking, traversing something. It's not the most efficient way, we know that. Do you have any idea how this could be impacted by your tool or your way of optimizing things?
Yes, thank you. Thanks for the question. I'm not seeing you. I'm seeing my question slide. Maybe some technical problems here, but yes, thanks for the question. It's very interesting. So we did, as I just mentioned, so we did some work on defining, let's say, a catalog of what we call energy smells. That some of those smells comes from Android performance issues reported by Google. And for each of those smells, we define a refactoring, and we automated this in a tool that was the result of one of my former PhD students, Marco Couto. So in that way, looking at source code, if for instance we didn't look like for these benchmarks, why, for instance, some of the Python programs we didn't have time are running a bit slower with power cap, faster with power cap than without power cap. Okay, that was surprising. I don't know if it's our programs that are to run so fast that there are some, I don't know, some overhead. But yeah, but we didn't look at the compilers themselves, and let's say I don't have recommendations, for instance, for a Python compiler developer, how they can improve the Python language in terms of making it greener or even faster. But the only thing I can say that is I don't see any fundamental feature on the language to be so slower than others in C. That's my opinion. Sorry.
Hi, João. This is Eric Van Wyk. I'm sorry you can't be with us here in Pasadena. It's been good to see you again. So, but I had a question about so you sort of organize this around different languages. Did you think about organizing this around different language features or characteristics? So it was sort of statically typed versus dynamically typed, garbage collection, no garbage collection, these sorts of things to sort of see what sort of features pop out as, you know, energy efficient or slow. I think we have guesses again, but I think the whole point of this is to get some numbers to see what really happens. So.
Thank you for your question, probably Eric. So, can you see my slide here?
Yeah, we can see it.
So we organized in terms of we grouped the language in terms of compile language using virtual machines, interpreted ones. We also in our original paper we divided them or grouped them according to the programming paradigm, functional, object-oriented. But you have this hybrid language that supports both, even for us. Okay, to classify a language as is it a functional language? Is it a OO language? It was not easy, and we got some comments from the reviewers in that time, as far as I remember. Yes, but it's a good idea. Of course, we could do it. Dynamic typing, a lot of mechanisms that we could probably, yeah, we could extend this with more languages. I don't know. Yes, it's a good idea. It's probably next year project for students. But there was an interesting colleague who did work on multi-objective optimization that it considered not what is here, energy, time, and memory consumption. He also had more attributes like popularity of the language and other more let's say non-metric, it's also metric, but different attributes of the languages, and he defined algorithms. So I want now, if I'm more interested in a language that consumes less memory but is more popular than other, and different and getting different rankings. Yes, but also we can, of course, we can also focus on features of languages. Yes, thanks.
Okay, is there any last question in the room? Maybe during the time that the next speaker is setting up the laptop.
Hi, João. Thomas here from Amsterdam. Unfortunately, you can't be with us here today. I wanted to ask about the particular value for the cap. So you mentioned that you tried some things out and settled on 15. I wondered to which extent this is like dependent on the types of programs that are used, or perhaps also whether when you experiment with the different values, whether you see the same relative results as you presented here today across languages?
Yeah, Thomas, thank you for your question. Yes, yeah, it's a good question. Well, if we think in terms of GCC or the -02 flags of GCC by default, okay, they are in general or in average they produce the most efficient binary program. Okay, but for particular programs, you can have a different order and a different set of optimizations, C optimization, that for that particular problem, that sequence produce a better program in terms of execution time than -02. I'm sure here is the same. I'm sure that there is probably some of these programs with a different value for the power cap will produce more or more greener executions, okay? But that will cost us, it will be unfeasible to do this. In all these programs, we have, let's say, 200 programs to run each of them with different power caps and see. But yeah, probably I'm sure we can improve on these results. Yes, like as I mentioned for -02, compiling flags. Yeah, but it will take more time. I don't know if the result will be that different. Probably, yeah, we can improve a bit, I'm sure. Thanks for the question.
Thank you very much, João. I think we can thank again the presenter. Thank you very much for this very interesting presentation, and we are looking forward to have the new results next year. We heard yesterday that the next